Some problems that we're going to be interested in will involve heterogeneities that are not symmetrically distributed around the column. This is an example where we have three cylindrically shaped heterogeneities that are just fairly arbitrarily located, at least with respect to the symmetry point. So if we imagine an axis of symmetry that goes along the column like this, that that little heterogeneity is set off at a radial distance out from the axis. This one is also set off a little bit, and this is set off a little bit. So we can't use the symmetry that we used in the 2D analysis, and we have to go to a fully 3D analysis in order to simulate this kind of a problem. So to do that, we'll go and open up a 3D model, and we'll select Darcy's law as the physics, and we're going to be interested in just doing a steady state analysis. So we'll pick the stationary study here, and we will open it up here, and the first thing that we want to start with is the geometries. So we'll select the cylindrical geometry, and we're going to keep the same specs of a 1-inch radius, so 254.0254 meters, and the length would be 0.2 meters. So there's the cylinder, and we can look inside it if we like by selecting this little, see, that's eyeball with a slash through it, and we'll select boundary there. And so if we do that, we make the boundary transparent, and we can look into the inside of the cylinder that we just created. So there's nothing there, but that's okay. We haven't put any heterogeneities there. What I'm going to do is set this problem up for just the homogeneous case, and it'll be then essentially the same as what we analyzed in some of the previous cases. But we'll do that just to get a feel for how to set up this 3D case. I'm going to do the fluid properties first, and then the matrix properties, and the porosity is 0.1, and we'll switch over to hydraulic conductivity, and we'll make it 1 e to the minus 6, 10 to the minus 6 meters per second. We also will need boundary conditions, and so for this case we'll just use the same ones that we had before. We'll use two pressure boundary conditions. At the top, I'm going to select the top there, and this boundary condition requires that the pressure is 0 at the top, and at the bottom we said it would be 2400 pascals, like so. And we need to have a mesh, so we'll take a look at the mesh. The mesh shows up on the sides of the model. We don't see the mesh internally in this view, but that gives us a feel for what the mesh looks like, the density of the elements in the mesh, and that'll be okay for our problem so far. We'll then go ahead and do the analysis, and the result is shown here. You can see the 3D problem is the results are shown here with these 5 cross sections. This is pressure that's being plotted, and we can also show this is just the default plots. The other default plot shows the pressure here projected onto the side of the 3D space. Okay, so that's the kind of result we expected. Let's also take a look at the flow rate. Remember, we analyzed the flow rate and for the 2D and 1D case, and we'll go and try that out by selecting the Darcy velocity magnitude there. Plot that, and here's the result. That's 1.22 times 10 to the 6 meters per second. That's the same result we got for the 1D and 2D cases. So that's encouraging, and you can see we have some different colors here, but the color scale doesn't really show any variability. That's because this is I don't know, this is just a plotting artifact. It's really a uniform velocity through the problem. Okay, so that all looks good, and this is basically still just a 1D problem, but we'll make it 3D by adding another cylinder. And so I just go up to Geometry, add the cylinder here, and the radius of this cylinder will be 5 millimeters, and the length is 2 centimeters. So if I fill that in and build all objects, then there's that little cylinder down there. We're going to want to move it up here into the column, and so we'll do that. I'm going to use this to press that button right there to orient this this view. And what I'm going to do is move it off center by a centimeter along the x-axis, and then I'm going to displace it like that much along the z-axis. Now, just for reference, this little symbol right here shows us the different coordinate positions. And if I build all objects, there's the heterogeneity that's inside of our column. All right, now we need to specify the properties of that heterogeneity, and we can do that by going back to the physics node and selecting fluid and matrix properties. And so now we need to select this little cylinder, and there are a couple of ways that we could do that. One way would be to go under selection. Here we go to all domains, and this is domain number 2, so we select all domains and then select domain 1 and press minus. That gets rid of the selection, and now we just have domain 2 selected, and you can see that it lights up to show that that's what's being selected. So it's going to be very important that we have the right domain selected, and you can check that by looking at the domain number here and seeing what's lit up. Okay, so this allows us to specify the properties for this domain separate from the properties in domain number 1. We'll keep the fluid properties the same, so the density will still be 1,000 kilograms per meter cubed, and the dynamic viscosity is still 10 to the minus 3. The porosity will be 0.1, and the permeability, what I want to do is have this be a low permeability zone. So we'll make it 1 e to the minus 8. That would be 1% of the permeability or hydraulic conductivity of the surrounding medium. Okay, so that's a reasonable contrast. We'll keep the mesh. This is a default mesh generator. The mesh is going to be changed because of this heterogeneity that we've added. Let's go and build the mesh like that. And now we can go and let's just try zooming in on this heterogeneity. You can see that it's been meshed separately with these much smaller elements. And there's of course a finite element mesh all through this 3D volume that just isn't showing up with this plotting. Okay, so now we can run this, and we run it, and there's the result. We're showing the velocity, and it all looks green here, but there's a little bit of a difference showing up. We're going to need to change the plot, I think, to really see the result. So we go here to slice, and the default is to have 5 slices, but I'm going to change it and just have 1 slice. I'm going to make the position here interactive. So there's the slice that goes right down the center, and our heterogeneity is over there. And I guess you can see a little bit of a different color here. So the velocity is affected by a little bit, but if we move this cross section over like that, now the cross section is going right through the heterogeneity, and we can see that this gives us a much better view of what that heterogeneity does to the magnitude of the flow. So within the heterogeneity itself, we've got this dark blue color, which is a low value of flow, and then we see above and below the heterogeneity there's a a bit of a shadow here of low flow velocities, and right at the corners there's a higher flow velocity, higher than just ambient. In fact, the flow velocity even on the side of the heterogeneity is higher than the ambient. And the reason for that is fairly straightforward. What we're doing is blocking the flow by making this region a low conductivity, and so the flow that would otherwise go through this region has to go around it now and go through this region here, and so that causes the velocity to speed up. Okay, so that's all pretty reasonable. It gives us a nice way to visualize the velocity field. Another thing that we might be interested in doing is using some streamlines to further improve our visualization of the velocity field. So if we go down here to plotting and the plot setup, if we add this streamline node, then what we need to do is go down here, and we're going to start the streamlines on the default. It's started on a selected boundary. So let me pick that boundary. The default is just 20 streamlines. So we'll do that. Let's just stick with the default, run it. And here are the streamlines. They're these red lines. Okay, so in the absence of this heterogeneity, you would expect the streamlines to be straight. And let's look down it. You can see that by and large they are pretty straight, but these streamlines that are close to the heterogeneities have this little bit of a bulge to them, and that's because of the effect of the heterogeneity causing the flow to go preferentially around the heterogeneity. This streamline right here that is going close to the center of the heterogeneity, it's affected the most. You can see that one right there. You could zoom in on that. So there's a streamline that really changes a lot as a result of this heterogeneity being there. So this streamline capability gives us the capability to visualize the pattern of the flow within 3D. All right, so that's pretty good. We've got this 3D heterogeneity, this cylinder that has a different hydraulic conductivity in the domain, and we've run the model with it. So that's pretty good, but now we want to put in a few more cylinders, and we want them to be in a specific place. What I have in mind is that I want to have these 3 cylinders, and I want to have one here, one here, and one here, and they're going to be separated by 120 degrees. And I'm not quite sure about what size I want, so I want to be able to adjust the size and the length automatically. So the way to do that is to set up the specifications for this heterogeneity using global definitions. And we'll do that by right-clicking and selecting a parameter, and let's call it het rad, the radius of the heterogeneity. So we'll enter 005, and down here in the cylinder, instead of typing in this number for the radius, I'm going to instead use the variable name. Okay, so now when I go and build the object, when I do it the first time, I get really no change because the value of het rad is the same as I was using 005. But let's double it. Let's make it 0.01. And now when I go and rebuild that geometry, I get a bigger heterogeneity. Okay, and of course I can change it back and rebuild it. And so this is how we're going to control the details of the geometry without, well, basically through variables. They have to be variables that are defined up here under global definitions. Okay, so let's see. We can put in some additional, well, I need 2 other cylinders. So what I'm going to do is take advantage of the ability to go right click and then hit duplicate. And then I'm going to do it again. So this gives me cylinders that basically specs that are copied from what I have here. So these are 3 cylinders that are defined with hetrad. And they have they have all the same x, y, z locations. So what I might want to do is, just so that I can see them, give them different z locations. That one 0.2, and this one would be 0.06, say. And build all objects, and so there they are now. There are those 3 cylinders. All right, so that gives us the ability now to have all 3 cylinders, and we want to be able to change the location around using variables. So the way that I did this is I came up with a whole set of variables, variable names, and calculations to get the location of these cylinders to be where I wanted them. And then I save those variables in a file, and I'm going to open up and use that file now. So I go up here to parameters, and I go here to open file, and I have a file called 3D flow parameters. So open that up and see that one that shows up as red. That's because that's a repeat of this hetrad variable name that I just put in. So I'm going to take that out. So here are the variables. There's hetrad and hetlen that we introduced already. And then I have these other one, hetrad position, cylinder length, cylinder radius, and so on. So what I can do then is use these to define the locations of these cylinders. Now, the way I did this when I set it up is I had one set of expressions here, one set of, there are a few equations where we're doing some calculations, and then I have all of the parameters here. So in addition to this, I've got another file that I call flow variables. I'm gonna open that up, and what this is, this has the lines from here to here, and that's x p1, y p1, z p1. This is the x, y, z location of the p1 cylinder. Okay, so this set of variables I use to set up the locations of the 3 different cylinders. And so what I'm going to do is I think the easiest way is for me just to delete these 2 cylinders that I put in. And here we just have 1 cylinder left, and I'm going to define it totally with these variable names. So I call it hetrad, let's call it hetlen. This is the x p1, y p1, and z p1. Okay, and if we go back to parameters, there the x, y, z p1, there's hetrad and hetlen. So I can now go and try it out. I'll go build all, and there's what I get. I'm going to zoom out a little bit. All right, so that's the location and the length. And then what I can do is just copy this. So I'm going to duplicate it, and I'm going to duplicate it again. So the way it's going to work is that hetrad and hetlen define the geometry of the cylinder, and then these things define the position. So the geometry is going to be the same, and the position, I'm going to just make this x p2, y p2, z p2 for this cylinder, and then this cylinder would be x p3 and so on, yp3, zp3. Okay, so now we should be able to build that and have our 3 cylinders. And so, okay, that's what we get. I think what I did was when I set this up, I set it up for a primary cylinder that was a little bit longer. So if we make the outside cylinder 0.3, then we have something that looks like that. Okay, and those are then positioned 120 degrees and staggered along the length. Now, if we wanted to go and shrink back the length, I think the way I set this up is if you go here, I have sill rad and sill length. So that's sill rad and the cylinder length. Okay, so there they are. And now, if I want to make it shorter, I just go here, the overall length, change it to 0.2. And then if I go and check that out, then I get that. So I've kind of shrunk down the position, and I think that I now need to shrink the overall length of the cylinder, of the little cylinders. So the heterogeneity length will make it half of that. And let's go and rebuild that like so. Okay, so let's see. That looks pretty reasonable. If we wanted to change anything, then we can just change them systematically by varying these parameters here. And I'm not going to go through the details of how I set up all of this. It's basically trigonometry, and it's something that you can figure out on your own. It's fairly straightforward, but it certainly does require a little bit of trial and error. So let's go and yeah, there is one more thing though that I want to show you, is because we're gonna have to set up the properties for these 3. So one way to do it would be to go back here to the fluid matrix properties, and we want to have all 3 of the domains. So if we get rid of that domain 1, then there's all 3 of the domains. And so that would be one way of doing this, and that's a pretty reasonable way. I think we can try running this study and see how that looks. So there we've got these 3 domains in there, and you can see if we zoom in, you can see the streamlines going around that heterogeneity. And we've got a couple of other heterogeneities in there that we can probably the best way to see that would be to move this slice. There you go. So there we can see the bottom heterogeneity, and so on. Okay, so that's I think pretty much what we were after. Let me just show you one other way of handling this kind of thing. What we can do is go here to definitions and include variables, and I'm going to include a variable that I call capital K, and let's call this capital K matrix. Well, let me see. I'm going to do it like this. I'm going to put in a variable, and I'm going to say that it only applies to the subdomain here, subdomain 1. Okay, and I'm going to have k 1 e to the minus 6. Okay, so capital K is often used for hydraulic conductivity, And what I'm going to do is go back here to the physics and erase this. This is where I have just set up the lower hydraulic conductivity right there for the different heterogeneities. So I'm going to go and delete that. And what I'm going to do instead is to go here to the matrix properties and put in this variable that I'm going to call K. Okay, so you can see that in the model it's also called capital K. So what we're going to do now is to go here under this definitions. We have a sheet of variables, and this variable that we've just defined is applying to domain 1, and it's saying that the conductivity K is equal to that. And let's call this variables in matrix. And we can also then have another page of variables that we'll call variables in heterogeneity. And that'll be K, and that'll be 1e to the minus 8. Okay, and what we need to do is say that this applies also to domains. And we're going to start off saying all domains, and we're just going to delete out domain 1. So now we've selected these 3 domains, and we've got a variable that we've defined as variable K, and it has that value when we're in these domains, and when we're in the matrix it has this value. So we've put in that variable name here in the physics, and now we can go and run this, and we'll end up with essentially the same result that we had previously, but we've set it up by defining these variables that are just this one variable K, that we put the variable name here where we've defining the value for the hydraulic conductivity. So instead of having a number, we have a variable, and we specify the value of that variable up here under definitions. And in this case we have 2 pages of definitions that apply to 2 different subdomains, and they define the value of the variable for that particular subdomain. So that's another way of handling heterogeneities within this 3-dimensional model.